here's the second kind of canonical way we're going to represent graphs in this class. And in this class, we call this an adjacency list. Adjacency list. So the way an adjacency list works is we're going to write down an array, or some people want to think of this as a linked list for each vertex. Right? In fact, linked list is generally all you need for this. So for each vertex, we're going to write down an array. So for example, we'll have an array that is associated with vertex A, an array that's associated with vertex B, one for C, and one for D. And then if I represent this as a linked list, what I'll do is I'll make that the first item in the linked list, and then I'll have a pointer to each of the other vertices that A is connected to. Okay, so I'll have A pointing to B, pointing to C, pointing to D. And so what this represents, what A's list represents, is all of the vertices that A is connected to. Okay, so this by itself is all of A's neighbors. Right, and so then B is going to have a similar list. So B is only connected to A and D. So it'll have a pointer to A and a pointer to D. Right? And notice that when I'm writing this thing here, I have A pointing to D. That's just a kind of a vestige of the data structure. It doesn't mean, it isn't representing that A is connected to D. Right? This is B's list. So everything in B's list is just telling me what B is connected to. So this list here is all of B's neighbors, right? And then C has its own list, and C is connected to A, and it's connected to D. And then D has its own list, and D is connected to everybody, A, B, and C. Okay, so so again, you can just follow this down. This is all of C's neighbors. This is all of D's neighbors. Okay, so you might look at this and say that doesn't look particularly friendly. Like it doesn't look like a really excellent way of writing a graph, representing a graph. But now let's think a little bit about why you would use an adjacency list sometimes rather than an adjacency matrix. Okay, so we'll spend just a very brief time, and we'll think about this much more later, but a very brief time on which one of these is better. Okay, so which representation is best? Well, suppose you have a graph that looks like this. Well, maybe I won't draw every single edge here, but suppose I had a graph that had, say, 6 nodes and many, many, many edges, right? It had all the possible edges that exist between 6 nodes. And I believe I'm missing several here, and I don't know which ones I'm missing for sure, but suppose I had what is called a complete graph on 6 nodes, right? So this is a complete graph on 6 nodes. Okay, how would I write an adjacency matrix for this? Well, I would write a 6 by 6 matrix, and I can even write this thing out, 6 by 6 matrix. And I would fill it with 1s. Right? So I'd have 0s down the diagonal, and then everything else would be a 1. Right? Here's my adjacency matrix that captures that graph. There it is. Okay, I just did it. I just wrote you the adjacency matrix. Okay, it just captures this graph. Okay, so that's fine. Now, what would the adjacency list look like? Okay, so the adjacency list. So here's the matrix. What's the adjacency list look like? Well, I'm still going to have 6 lists. So I'll have 1, 2, 3, 4, 5, 6, and then for each one of these, I'm going to have a list just enumerating every other node, right? So this one I'll have 2, 3, 4, 5, 6. This one I'll have 1, 3, 4, 5, 6, and so on. Okay. So the space requirement for these two representations is identical. Okay. How many elements are in both of these? Well, there's exactly v squared elements, right? So both of these require v squared elements. So both representations require v squared elements. Okay, so there's no obvious reason to use one over the other, at least from a space requirement, from a space requirement standpoint, when the graph is complete. So now, what if I had a graph that was not complete? Okay, what if I had a graph that looked like this? And so this is a kind of graph, and it'll have the same number of nodes. This is a kind of graph called a star graph, and it's called a star graph maybe for obvious reasons, right? I could rearrange this so that there's one node in the middle and then a whole bunch of points of the star pointing off from it. Okay, so this is called a star graph. How would I write an adjacency matrix for this graph? Well, again, it's going to be a 6 by 6 matrix. And so I'm going to be extraordinarily sloppy here, but it's going to be a 6 by 6 matrix with some ones and zeros, and I could fill the diagonal with zeros. And now what edges exist? Well, let me call this guy 1. So 1 is connected to everybody. So I'll have 1s across that row, and because it's undirected, I'll have 1s down that column. And then everything else is 0, because those are the only edges that exist. Okay? And so how many numbers do I have to store? We could think of it as how many bits do I have to store to represent a star graph as an adjacency matrix? Well, it's still v squared bits, right? Adjacency matrix is always going to be size v squared, no matter what, right? So this is still size v squared, okay, for an adjacency matrix, right? Following. So now what about the adjacency lists? So if I were to write this as an adjacency list, what would I write? Well, I'd say I'd have my node 1, and node 1 is connected to 2, 3, 4, 5, and 6. And then my node 2 is connected only to 1. Node 3 is connected only to 1. 4 only to 1. 5 only to 1, and 6 only to 1. Right? So I would essentially, in my adjacency lists, I would save all this space. Right? This is saved space. Okay? And so the amount of space that's required to store the adjacency lists still depends a little bit on v, right? So I mean I do need exactly v lists, right? So if v is huge, if there's tons of vertices, you know, I'll still need, you know, as many lists as there are vertices. So if I'm thinking about how much space is required here, I'll have v lists, and then each list will capture exactly, or I should say, each edge appears in at most 2 lists. Okay, so each edge appears twice, right? So what do I mean by that? Well, let's think about this edge. So the edge between 1 and 2, well, that appears here, and it also appears here. Okay, so each edge, but it appears nowhere else, right? If I removed that edge, then what that would do is it would take this out and it would take this out. Okay, so let me just unmessy this up a little bit. But so what that means is that the space required for an adjacency list representation is 1, the size of the vertex set, because we've got v lists, and then 2 times the size of the edge set. Okay. And so we can write this in big theta notation as it's proportional to v plus e. And remember, when we're talking about big theta, plus basically means max, right? So whichever is larger, the vertex set or the edge set, is what drives the space complexity of adjacency list representations here. So an adjacency list, for a sparse graph that has very few edges, ends up being a very efficient way of storing the graph. Whereas an adjacency matrix is always v squared no matter what, right? Even if you have a very sparse graph, you still have to write those zeros in memory somewhere. You know, and it turns out that when people try to write matrices, when people come up with special data structures for representing very, very sparse matrices that have lots of zeros, what they literally do is this, right? They actually represent the matrix as an adjacency, essentially as an adjacency list. Okay, so the basic takeaway is the choice of data structure does actually affect the space required to store the graph. For very sparse graphs, you'll be a little bit better with an adjacency list representation. But there's actually some fundamental reasons why you would want to use a different representation as well. So for example, why you would want to use an adjacency matrix even for very sparse graphs. And we'll talk a little bit about those as we move forward.